Now the continuing the same. Now till now we have learned how to find out the minors and the cofactor. Relating the same topic, we are going to find out the adjoint of a square matrix. That is very much important. The word is here adjoint of a square matrix. Let A equal to Aij be a square matrix of order n. Then the adjoint of A is defined another square matrix of the same order, which is the transpose of the square matrix capital Aij. Capital Aij means cofactor, small aij means the element, where Aij denote the cofactor of Aij in the determinant of A and written as adjoint of A. So now here in the very simple words we can define how to find out the adjoint of a matrix. Adjoint of a square matrix A is obtained by replacing each element of A by its cofactor and then taking the transpose of the matrix so obtained. It is known as what? Adjoint of a matrix. It's in very simple. What do we have to do? If we have to given a square matrix, we have to replace the each element of the matrix by its cofactor and then we have to take the transpose of the matrix so obtained. It will give us the value of adjoint of A and written as adjoint A. Let us see by the example how to find out the adjoint of a matrix. Let me consider first a matrix of order 2. I have taken the matrix of order 2. Now I can find out the cofactor of each element. For example, A11. It means again the capital alphabet stands for what? The cofactor of the first element, A11. Now we have to find out its what? Cofactor. Now 1 plus 1 is an even power. So minor and the cofactor are both are the same thing. Now we have to find out the cofactor of this element. Again by hiding this row and this column we left with what? Minus 4. So A11 equal to minus 4. Then A12. Again it is power is an odd. It means we have to multiply the minor by the negative sign. Now A12. Again deleting this row and this column we left with what? 3 and multiplied by the negative sign because this power is an odd. Similarly A21. A21 again the power is odd. Now A21 again hiding or deleting this row and this column we will left with 2. As the sum is what? Odd. We have to multiply by the negative sign. Then similarly A22. Again deleting this column and this row we left with what? 1. So A22 equal to 1. But take care, whenever the sum of the indices is odd power, we have to multiply the minor by the negative sign. If the sum of the indices is even power, then the minor itself is the cofactor. And what we have to do? Now we find out the cofactor of each element of the given matrix. Now we have to replace each element by its cofactor. Now we are getting this matrix. Now we are taking the transpose of this matrix. We are getting the value of the adjoint of A. Already I have told you how to find out the adjoint. What do we have to do? We have to replace the each element of the given matrix by its cofactor and then taking the transpose of the matrix so obtained is known as what? Adjoint of the given matrix. So let us consider a matrix of order 3. Now here it is a matrix of order 3. Now again we have to find out the cofactor of each element. Now let us see, consider first element A11. Its cofactor will be what? Now we have to find out the cofactor of this. Again hiding this row and this column we left with 5 3 is 15 minus 0. It is equal to 15. Then A12. Again here the sum is odd. We have taken here the negative sign. So A12 again hiding this row and this column and by cross multiplication 0 into 3, 0, 2 into 0, 0. We are getting here 0. Then A13. A13 is this element. Now here again hiding this row and this column by cross multiplication this. We are getting what? 0 minus 10 equal to minus 10. Similarly A21. This element again hiding this row and this column. Now here the power is what? Odd power. We have to put the minus sign. Now we are hiding this row and this column. 2 3 is 6. 6 minus 12. Minus 6 minus minus plus. So it equal to 6. Similarly, A to 2 is this element, and now again hiding this row and this column. 3 minus 6, 3 minus 6, so it equal to minus 3. Similarly, A to 3 equal to 0. Similarly, we can find out the cofactor of the element of the third row by the same way. A31 equal to minus 15, A32 equal to 0, and A33 equal to 5. So we will find out the cofactor of all the element of the given square matrix. Now we have to replace each element by its cofactor, and this matrix is obtained. Then we have to take the transpose of this matrix. It will give us the value of the adjoint of a matrix. Now listen again how to find out the adjoint of a matrix either of order 2 or either of order 3. What we have to do? Firstly, we have to find out the cofactors of each element of the given matrix. Then we have to replace each element by its cofactor, and then taking its transpose will give us adjoint of a square matrix. Now the next is here the inverse of a square matrix. Inverse of a square matrix written as A inverse. Written as what? A inverse. If A and B are two square matrices of order n such that A into B equal to B into A equal to In. In means identity matrix of the same order. If the product of any two square matrices of the same order is equal to identity matrix, then each one is called the inverse of other. So here A into B equal to B into A equal to In. In is what? Identity matrix. Then B is called the inverse of A and vice versa, or we can call A is the inverse of B and written as B equal to A inverse. Now B equal to A inverse, using again this A into A inverse equal to A inverse into A equal to In. This is one of the important result. Now here the necessary and sufficient condition for a square matrix to be invertible is that A should be non-singular. It means determinant of A is not equal to 0. Or we can say inverse of a matrix only exists when the determinant of A is not equal to 0. Only then the inverse will exist. If the determinant of a square matrix is equal to 0, then we can say the inverse of that matrix will not exist, and A inverse is given by adjoint of A upon determinant of A. So therefore we will say the determinant of A cannot be equal to 0, because we know determinant can never be equal to 0. So therefore by definition A inverse is find out adjoint of A upon determinant of A. In the previous question we have find out what? Adjoint of a square matrix of order 2 and the adjoint of a square matrix of order 3. Now if we divide those values of adjoint by its determinant, then it is known as what? The inverse of the given matrix, and it is always unique. Let us consider the previous example. Now in the previous example we have to given a square matrix of order 2 and we have find out the adjoint of that matrix that I have explained earlier. Now what we have to do to find out the inverse? First I will find out determinant of A. Determinant of A is minus 4 minus 6 minus 10. Now it is not equal to 0, so we can write A inverse exists, and the value of A inverse is given by adjoint of A upon determinant of A. Now determinant of A value is what? Minus 1 by 10. Adjoint we have find out earlier, minus 4 minus 2 minus 3 1. Now we have to divide each element of this matrix by minus 10, and we are getting here 2 by 5, 1 by 5, 3 by 10, minus 1 by 10. This is known as A inverse. It means what you have to do, whenever you have to find out the inverse of a matrix, in the first step we will find out the determinant of A. If determinant of A is not equal to 0, only then you can find out the inverse of a given matrix by finding out its adjoint. Adjoint find out. What do we have to do? We have to find out the cofactor, then take the transpose. It will give us the adjoint of A. Then dividing the each element of adjoint of A by its determinant, we get the value of what? A inverse. Let us consider the another question. Let me take a square matrix of order 3. Earlier we have taken it. Now first what I have to find out? I have to find out the determinant of A. Now I am going to find out the determinant of A by expanding it by second row. Why I have choose here the second row? Because in the second row only first element and the third element is 0. Only we are having the second element of the second row, that is given to be 5. Always whenever you have to find out the determinant of a square matrix, we always prefer that row or that column which has maximum number of 0, because 0 into something is 0. It makes our calculation easy. Listen again. Whenever you have to find out the determinant of a square matrix, we always choose that row or that column which has a maximum number of zeros. Maximum number we can have only 2. We cannot have all the 3 zeros should be there. If all the elements are equal to 0 of any row or column, then the value of determinant should be equal to 0, because 0 into something is always 0. Now I am going to find out the value of this determinant by expanding it by second row. Now as usual we have to find out the first element. 0 into something, it will be 0. Then what? It will be started with negative sign. First we have to minus 0 into something, it will be 0. Then the next is plus 5. Plus 5, again we are hiding this row and this column. We are getting what? 3 minus 6 equal to what? Minus 15. Now the determinant of A equal to minus 15, not equal to 0. So we can find out A inverse exists. Then we will find out the adjoint of A by finding the cofactors and taking the transpose. This is the adjoint of A. Therefore A inverse is adjoint of A upon determinant of A equal to minus 1 by 15, finding the adjoint and then dividing the each element by minus 15, we are getting the value of what? A inverse here. So this is the simple way to find out the A inverse and adjoint. Now just listen, the cofactor of the element of a square matrix, then adjoint of a square matrix, then A inverse of a square matrix. All these three things are very much related with each other. Now here let us see some properties of the adjoint of A and properties of A inverse. They are helpful in sometime solving the question. Let us see all the properties. The proof are given in the book. We can go through the proof later on. First I am only discussing the property of adjoint of A. Let us see the first property. Let A be a non-singular square matrix of order n by n, or you can say order n. The first property is here A into adjoint of A equal to adjoint of A into A is equal to I. First property is here A into adjoint of A equal to adjoint of A into A equal to I. The second property is here determinant of adjoint of A. Determinant of adjoint of A of order n is equal to determinant of A raised to power n minus 1. Third property is determinant of A into adjoint of A is equal to, it can be written as the product of determinant of two square matrix can be written as determinant of A into determinant of adjoint of A. Now determinant of A as it is, and determinant of adjoint of A can be written as determinant of A raised to power n minus 1. So determinant of A into adjoint of A is equal to determinant of A raised to power n. Here if only we are having determinant of adjoint of A, then it is determinant of A raised to power n minus 1. Here we have find out the determinant of A into adjoint of A is equal to determinant of A raised to power n. Similarly, the next is adjoint into adjoint of A. Adjoint into adjoint of A. It is equal to determinant of A raised to power n minus 2 into A matrix itself. Then here again the same is here. Determinant of adjoint of A into adjoint of A. In this property if we are taking the determinant, then it becomes equal to determinant of A whole power n minus 1 square. Then the sixth property is adjoint of A dash equal to adjoint of A dash. It means they are interchanged. Adjoint of A dash is equal to adjoint of A whole its transpose. And determinant of A into B, adjoint of A into B equal to adjoint of B into adjoint of A. Let me explain it again. The first property is here, A into adjoint of A equal to adjoint of A into A equal to I. Second is here, determinant of adjoint of A equal to determinant of A raised to determinant of A power n minus 1. Then the second property is determinant of A into adjoint of A is equal to determinant of A raised to power n. Similarly, adjoint into adjoint of A is equal to determinant of A raised to power n minus 2 into A. Similarly, we are taking here adjoint of determinant of adjoint into adjoint of A is equal to determinant of A whole power n minus 1 square. Adjoint of A dash equal to adjoint of A dash. Adjoint of A into B equal to adjoint of B into adjoint of A. On this property, sometimes the question of 1 or 2 marks are asked in the exam. You have to keep these properties in the mind. Similarly, let us see the properties of inverse of A. Again, the very first property, inverse of A into B equal to B inverse into A inverse, where A and B are non-singular square matrix. Second is again continuing the same, A into B into C inverse is equal to C inverse into B inverse into A inverse. It means these are multiplied in the reverse order, as A into B inverse into A inverse, A into B into C inverse equal to C inverse into B inverse into A inverse. Similarly, A raised to power n inverse is equal to A inverse into A inverse whole power n. Next, if AB equal to AC, just see it here. If AB equal to AC, then B equal to C, only if determinant of A is not equal to 0. And this is known as left cancellation law. This is known as left cancellation law. If AB equal to AC, we are just from the left hand side, we are cancelling A. This implies B equal to C. So this is known as left cancellation law. And similarly, if B A equal to CA, then B equal to C. This is known as right cancellation law, but only this like this when the determinant of A is not equal to 0. And the next is the fifth property, A inverse of A transpose equal to what? A inverse transpose. Listen it again. A transpose inverse is equal to A inverse its transpose. And the last is here, determinant of A inverse is equal to determinant of A inverse. Again, determinant of A inverse is equal to determinant of A inverse. And next is here, if A is a symmetric matrix, then its adjoint and A inverse are also symmetric. If A is symmetric, then its adjoint as well as A inverse will also symmetric. These are all the properties of adjoint of a square matrix and inverse of a square matrix. Now let us see the questions based upon this. Now we know the meaning of inverse of a matrix. Let us use it. Now here the question is one of the important questions based upon the inverse. Show that this square matrix satisfies this equation and hence find A inverse. In the exercise, I think 3.3 or 3.2, when we learn how to do the multiplication, our question is still here. If A, show that A equal to this satisfy this equation. And now that this question has been extended, first we have to show this satisfy this, and hence using this equation we have to find out A inverse. Now let us see the question. Now first we have to show that this satisfies this equation. Now when we putting this, it becomes A square minus 3A minus 7I. Earlier we have done this question up to now. Now the left hand side become A square minus 3A minus 7I. Putting all the values, A square means A into A. Putting the value of A, putting the value of I, it is the identity matrix of order 2. Then simplifying it all, we are getting it is equal to 0 matrix. Now using this equation, now we have to find out A inverse. Otherwise we can find out the A inverse by using what? Cofactors, then finding the adjoint, and then we can find out the A inverse. But here it is mentioned in the question, only by using this equation we have to find out A inverse. Now how to find out A inverse using this equation? Let us see. First we will see either A inverse is existing or not. We will find out the determinant of A. Determinant of A is what? Minus 10 minus minus plus minus 10 plus 3 equal to minus 7 is not equal to 0. So we can say A inverse exists. Now let us see how to find out the given equation to find out A inverse. Our equation is A square minus 3A minus 7I equal to 0. First we have to simplify this equation such that in the left hand side or the right hand side we get only I. We have to simplify this equation by taking the terms to our left hand side or the right hand side. So on one side we get, or the generally in the right hand side we get only I. So it can be written as A square minus A common A minus 3I, because a constant quantity does not have any meaning in the case of matrices. When A is common we left with A minus 3I equal to 7I. Now taking this 7 to this side we are getting here A into A minus 3I upon 7 equal to I. Now earlier whenever we were discussing the definition, A into A inverse equal to I, we know it. Now comparing these two equations, A equal to A, I equal to A. Therefore A inverse is A minus 3I by 7. Putting the values 1 by 7, putting the value of A here and putting the value of I here. Simplifying, we are getting the value of what? A inverse. So this is a very much important question based upon it, but care should be taken. Only by using this equation we have to find out the A inverse. So this is all about the today lecture. Today we have learned how to find out minors of the elements of a square matrix, then cofactors, then we find out the adjoint of a matrix, then we find out the A inverse of a matrix and their properties, and by the application of these all we can try the exercise question.